Okay, folks, it's 8 a.m., so we can get started. Welcome to lecture number 2, where we're going to continue talking about reactivity of heterocycles, and this is going to aid you in the process of substitution once you learn how to make the heterocycle, which we won't cover for another few lectures. So last time we talked about a number of features of how to substitute a heterocycle, and today we're going to start with what about electrophilic attack at carbon. And the canonical representation for Friedel-Crafts, of course, with the regular benzene ring that you learned back in undergraduate chemistry is shown here through the famous sigma complex or Weyland intermediate. And when you get to heterocycles, though, things change up a little bit. For example, as we talked about at the beginning of yesterday's class, nitrobenzene and pyridine can be thought of as synonymous. The only difference is that when you treat pyridine with an electrophile, of course, as we're going to see today, it goes very quickly at nitrogen. I think we talked about that last time as well. So you're not going to get Friedel-Crafts on a pyridine very easily unless you start putting electron donating groups on there, such as an aminopyridine, which then undergoes bromination, for example, with pretty good ease. And then if you talk about the pi excessive heterocycles, we talked about that on Monday. For instance, pyrrole is going to go at C2, indole is going to go at C3. We talked about the reason for that. Furan, a little bit less likely to undergo Friedel-Crafts because you're there's not that much, it's not as pi excessive as those pyrrole type heterocycles, and then thiophene sort of a baseline. And then we also talked about how to take a pyrrole and invert its selectivity by simply adding a sterically blocking group like a TIPS group. But it can also be done with things like a Tosla group will also get you to C3 instead of C2. So based on this and based on the ideas we talked about on Monday, where you can take two types of nitrogens and the reactivity can be viewed as a superimposition or combination of the two reactivities that are engendered by those two types of nitrogens, we get to problem of the day number 1. And perhaps it's worthwhile to mention that we have approximately 145 circulating pyridoge currently. A lot of people have a good amount of pyridoge, so I'll let you volunteer for this problem of the day, or I can call on someone if no one sort of offers a suggestion for this.
I can do it.
All right, what do you say, Alex?
So you have both pyridine and pyrrole like nitrogen. So you'll end up with bromination at the C2 position because of the control of the pyridine selectivity.
Great. So that's exactly how to rationalize it. You don't need to memorize it. You don't need to go into any FMO theory to do it. You just memorize understand these simple rules of what a pyridine nitrogen does and what a pyrrole nitrogen does. And yeah, I think that's exactly what's going to happen. Now, a frequent consulting question that I get over the years is this one. They have a complicated heterocycle and they wonder, where is electrophilic aromatic substitution going to go? Where is bromination going to go? And what are some ways that you would think about rationalizing where these might go? It may be based on first principles. Do you have any idea to begin with? Let's look at this structure. What are some possible sites that you might worry about if you're a medicinal chemist looking to do Suzuki's or Buchwald's or whatever, and you're worried about where your halogen is going to be installed? What do you think, Jun Chen?
I think it will go 1 because that's the only way you can draw some reasonable resonance structure, right?
Okay, you're going to go for 1, absolutely valid, a good choice. Any other suggestions? Do you agree with that, Aaron? Or perhaps Kelly? Do you agree with Jun Chen's idea?
You could also
C1?
brominate at C6 because it's kind of like in the 3 position of a pyridine twice.
Are there people who agree with Kelly or Jun Chen's location?
I agree with Kelly.
Agree with Kelly. Anyone agree with Jun Chen?
I mean, I think both of those would be the first I would guess, just because one feels right for some reason. And 6, I guess electronically maybe ortho to the aniline, yeah,
Yep.
type of nitrogen. Sorry, but if you look at the top heterocycle, maybe it's not so prone to attacking bromine because of this cyano group. They're pulling electrons out, but I guess it's tough to say.
It's tough to say. Yeah, I'm not going to give you the answer yet. How do you like that? We're going to go to the next one. Brendan, since you're already unmuted, what do you think of the next one?
I guess I only have 3 choices there, so I get a 33% chance.
Yeah.
Maybe C. Maybe C2.
Anybody disagree with Brendan here? Does anybody want to go with C1 or 3? Tim or Simona or Ellie, anyone want to opine on if they have a differing opinion on this?
I would also be kind of split between C2 and C3. You have like the Pearl-like reactivity with C3, but you also have the pyridine reactivity with C2. So it's kind of a toss-up for me.
Kind of a toss-up, yeah. So the right answer for these is C6 for the first one, and for the second one, C2. But the problem is you can rationalize it along the lines of the ways you folks rationalize it, but it's ambiguous, isn't it? And if you're a medicinal chemist, how do you plan out a route where at the very end you just have to sort of hope and pray that you're right, and maybe pull the department and use that as your way of determining the answer? Luckily, there is a better way of doing this, and it's a method that I really, really like because it doesn't require extensive computation. And it comes from this JOC paper from some former students, and I've given this out a lot in consulting sessions. It works really well. Everybody has ChemDraw, well, most people do. And so you can simply use the proton and carbon prediction software in the ChemDraw that is instantaneous, and use that to justify where the site of halogenation is going to go. And just by looking at the lowest proton and carbon shifts, that will basically tell you. And in this paper, they do a huge study of all these sort of literature examples. They do some of them in the lab themselves and find that there's a really great correlation. And the sort of take-home message of this is that for the types of heterocycles you see here, this method works really well. For these ones, however, there's sometimes a discrepancy between the prediction software in ChemDraw and the actual result you get. And in that case, it's probably better to use a HOMO-map. If you're in a big company, you have a computational department, they can do that for you. And that would be the way of a medicinal chemist planning out a route with a late stage halogenation and a poly-substituted heterocycle, and having confidence on the location of the halogenation. What happens when you take a pi-excessive heterocycle like pyrrole and you simply submit it to treatment with acid? Yesterday, someone already suggested that this type of thing would happen. But does it stop there? Has anyone ever done anything with pyrrole in the lab?
Well, it will get polymerization.
Aha, you get polymerization. So what must be happening is that one molecule does what I show here, and another molecule of pyrrole comes in and says, hey, I don't want a proton. I want one of these folks. And often when you, of course, take pyrrole and you leave it exposed to the air, or you leave it exposed to just let it sit around for a while, the bottle of pyrrole you get is usually very dark color. And the reason for that is it's polymerizing. It's also reacting with oxygen through a single electron transfer mechanism. And so that's what happens there. But there's a useful way to capitalize on this type of interesting reactivity. So let me ask you, Nguyen, does the same thing happen with the bromopyrrole here? What do you think might happen with weakly acidic conditions?
You will get the rearrangement of the bromine atom to the 3 position.
Brilliant. So this is our first exposure to halogen dancing. And it can be rationalized.
I mean, usually you will need some substitution on the nitrogen of the pyrrole to make the thermodynamic equilibrium favor the 3 position, right?
It actually works with NH, but usually, yes, you'll have an N-alkyl group. But the important thing to remember is that these dancings do work really well. There are some dramatic examples of the dance. For example, you can take this compound, treat it with acid, and you can actually get that compound to arise as a result. It's not limited to bromine, so there's other types of heteroatoms that will do the same dance. Most popular is sulfur. So a sulfur atom will also do the same type of dance. We will talk about halogen dancing quite a bit in this class, particularly on Monday, but it's going to be in the context of a different type of dancing that involves anions rather than cations. But this is a useful one to keep in your back pocket to remember. Of course, the conditions here are carefully controlled so that you don't get black tarry mixture of products. But it is a useful tactic that has been seen quite a bit. So we're going to cover some total syntheses. And I don't want the sort of medicinal and process and industry folks that are on the line today to be too bored by this. But there are some really important take-home lessons from looking at these natural products that can translate into your own programs. So let's take a look at the example of Prodigiosin. It's a pretty famous little alkaloid. It dates back to biblical times. It was produced by bacteria. And actually, Alexander the Great's most difficult conquest apparently came as a consequence of this alkaloid, because there was a piece of bread that was apparently bleeding, and that was a message to the Macedonian troops that victory was theirs if they just went out and fought. And so Alexander the Great then went out and did what he did, and I guess that Western civilization history followed after that. So there's been victories associated, but also mass casualties. So the famous mass of Bolsena, if you're Catholic, where some bread was again found bleeding, was named a miracle and started the festival of Corpus Christi, but it also led to a lot of mass executions of Jewish people because they viewed the bread bleeding as a sign that there was something the matter with them. So all of this because of a little red alkaloid. Now, how do you make this compound? Are there disconnections that you can think of for a convergent retrosynthesis of this that would simplify the picture, taking advantage of innate reactivity of a pyrrole? I'll make it easy for participation by maybe labeling some carbon atoms. Maybe Sung Han over in Florida can help us out. What bond do you think might be an interesting bond to break?
I guess 7 and 8. Maybe you can use the similar condition you mentioned above.
Okay. 7 and 8, that sounds pretty good. We're going to use the conditions we talked about, so that's great. That's a great idea. Are there other bonds that we can break?
2 and 3.
Oh, that's awesome. A lot of Dogecoin coming your way, my friend. All right, so that gives us 2 intermediates. One of them is the rather electron-rich pyrrole here. And the other one, when we cut that bond, what is left in its wake is going to be an aldehyde. That will be compound B. So let's go forward with the root. And as Sung Han mentioned, we can use the same chemistry we just talked about. And these two will condense together very easily to give us the bis pyrrole adduct shown here. Just going to label The E is ester. And when we take this compound and treat it with palladium on carbon and heat, what do you suppose is going to happen? We need a nice process chemist for this one. How about Daniel? There's your hint. The carbon skeleton is still there. I'll even throw the ester on there and I'll give you the methoxy. How's that?
Yeah.
What's going through your mind? Are you thinking like, where's the hydrogen gas?
Yeah, that definitely passed my mind, but I would think.
Hey Daniel, I'm going to do you a favor. I'm going to give you some hydrogen. I'm going to give you some hydrogen gas. Watch what I do. All right, now, how about that? There's your hydrogen. I'm not adding it.
You're taking it away.
I'm taking it away. So where can I take it from? Where in
Perhaps
this molecule can I take hydrogen gas from? Where am I going to get it?
on the to form the from the new heterocycle that you added. At the I don't know what position that's called. So I was thinking from the 1 and 2.
Well, if nitrogen is 1 and then 2 next to it, yes, that's exactly right. And you'll do that not once, but twice, and that will give you your fully aromatized pyrrole. So dehydrogenations like this are very common in heterocyclic chemistry. The pyrrolidine is a fantastic hydrogen donor. So you can do easy hydride transfer by pushing electrons in here, kicking out hydrogen, and do that not once, but twice, and then 3 times, and then 4 times, and then you've got a fully aromatic pyrrole. Okay, so this is you're going to see this quite a bit. This is a good way to remember that heterocycles, unsaturated, or saturated heterocycles love to be fully unsaturated, and you can do that with things like DDQ. Sometimes oxygen will do it. Various metals will do it, and will extract hydrogen from these compounds. So yeah, you're just removing hydrogen. Great. Now in the next step, we're going to treat this compound with hydrazine, then tosyl chloride, pyridine, and then we're going to heat it up with sodium carbonate. So in the first step, all we're going to do here is make the corresponding semicarbazide. There's nothing else to do than to simply add in there. And now we treat that with tosyl chloride, and hopefully Camille can help us out with what happens there.
Do you tosylate the terminal nitrogen?
Awesome. And why don't you take us home?
And then in the presence of base, you eliminate and then there's loss of N2.
Awesome. This is the famous McFadden-Stevens reduction, and that gets us to the corresponding aldehyde, which is super convenient because if we go back here, wow, that's compound B. That's what we needed. So that gives us compound B, and B can be combined with A to give you the product. Now we need to figure out a way to make the Yes, we need to figure out a way to access. Oh, it looks like I gave the mechanism already. Problem to number 2. So great, wonderful. So Camille, you got full credit for that. Problem today number 2 we just covered. Well, we covered the second part here. Great. Okay. So let's move on to problem of the day number 3, which is the famous synthesis of Keterolac, which is a non-steroidal anti-inflammatory agent that is still prescribed today and involves some very interesting reactivity lessons that start with problem of the day number 3. So how about Nathan in California can help us out with this one? We treat this.
So the dimethyl sulfide will be activated with the NCS reagent by getting chlorinated.
Okay.
And then the pyrrole can do like SN2 type reaction at the 2 position to kick out the chloride.
Okay.
And then the counter anion is going to pick on the methyl group.
Fantastic. Now, when you take this pyrrole and you expose it to POCl3 and this benzimide, you make an intermediate Vilsmeier reagent that is highly activated towards Friedel-Crafts. And that gives rise to simply the benzoylated product with the regiochemistry you would predict. And now, when you treat this with a Meldrum's acid-derived cyclopropane and base, something interesting happens. So hopefully, Ellie, perhaps, or Taiwei can help us with what's going on here. Sodium hydride does what?
It deprotonates the nitrogen of your pyrrole.
Now what do I do?
Then I think you can attack the cyclopropane, like the, yeah, exactly.
Awesome.
And then that will open up.
Okay, now we're going to treat this with an oxidant and then some sort of base. So what's going on here? What is there to oxidize?
You can oxidize the sulfur to the sulfone.
And then, Kelly?
And then you can deprotonate with base, like alpha to the Meldrum's acid moiety.
Yes.
And from there, you can kind of do like an SNAR at the carbon where the sulfur is.
Fantastic. And after hydrolysis of the Meldrum's acid derivative treatment with base, you get a decarboxylation that gives you Keterolac. Let me ask you a question, Kelly. Why can't I make the anion here and just do a SNAR straight on that?
I don't think that's a good enough leaving group with
No.
sulfur in that oxidation state.
No, that's correct. And it can sometimes be good enough if you've got pyridine-like nitrogens, but in general, to activate those thiomethyls, you're always going to want to oxidize them to the sulfone, and then you can do your addition elimination. But this is an exception to the rule that we talked about before, where addition, elimination, SNAR reactions don't work well on pi excessive heterocycles. The only reason this one is working is because we've got this electron withdrawing group at a position which can be in resonance with, in conjugation with that leaving group. All right, fantastic. So there's some interesting reactivity lessons that go back to the history of organic chemistry, starting with Woodward's famous synthesis of chlorophyll. And in order to go through this one, we'll go through it kind of rapidly. We'll start on the left-hand side here. This pyrrole bearing an amino group is treated with HBr along with this aldehyde. And what this accomplishes is just a protonation of this amine first, and then a Friedel-Crafts of the type that we saw with prodigiosin after reduction with borohydride, giving us the intermediate here. Now let's take a look at the right-hand side one. I need help with this one. So when this chloropyrrole is treated with the other pyrrole shown here, let's call this A and B, treated with compound B in the presence of HCl, somehow this adduct is formed. It looks like some sort of SN2 reaction, but I need help to understand what might be going on here. Maybe Tim can help us to understand what's going on.
Yeah, sure. So I don't think this is SN2, but I think if you push arrows from the pyrrole, you can actually kick out that chlorine to make a pretty hot electrophile. That exocyclic olefin can then be the electrophile for nucleophilic addition at C2 of the pyrrole you're adding in.
And this type of thing is a type of quinomethide. And quinomethides are super duper important in medicinal chemistry. In a lot of drug discovery, they bear their head in many different ways. They're used as constructs for bioconjugation. Many of the analogs out there for antibody drug conjugates use quinomethide chemistry in order to release cargo through a self-immolation mechanism. But there's a lot of mechanistic problems and consulting problems that come from a understanding of when you can make quinomethides. They're found all over the place. So this is a key concept and will form the basis of the first consulting question that we'll get to in just a moment. So thanks, Tim, that's exactly right. Following that, what is done is a simple Friedel-Crafts, and then treating this compound that results from the Friedel-Crafts with sodium hydroxide liberates this malonyl dinitrile adduct by simply, it's a protecting group for an aldehyde. So all one does there is a Michael addition, retro-aldol, you liberate malonyl dinitrile, and that gives you your aldehyde. And then they found that when they tried to take this compound and put them together directly, it was unfortunately kind of messy. So what Woodward did was a workaround where he formed first the thioaldehyde here, and he found he could do that using ethylamine, acetic acid, and then treatment with H2S. That formed selectively, although you can get, imagine, imines forming here and here, it formed with H2S selectively the thioaldehyde. Yeah, there's a bit more nuance to this, but the bottom line is the thioaldehyde is formed, and that gives way to the selective condensation between these two units here. After union give out the precursor to chlorophyll. Well, so where does this play into the real world? Well, we, a few days ago, got a nice consulting question from a big company that will remain unnamed and a person that will remain unnamed. But because they submitted the consulting problem, they are going to get 100 Dogecoin. So thank you very much for that. Maybe you can buy a t-shirt later on in the course or something with that currency. So the consulting question was as shown here. They needed a modular synthesis of a benzimidazole that we haven't talked about how to make yet. And the substituents can't tolerate highly acidic conditions. And when they tried this literature condition, where they were condensing this diamino trifluoromethyl benzenoid with this ester, what they were getting instead of the desired product was this ester type or acid type product. So based on what we just talked about from this ancient chlorophyll example, maybe Tim can continue to tell us what happens based on his answer before.
Okay, sorry, I had a separate idea for how we could make this. So were you referencing making the quinomethide?
Yeah, so CF3 groups that are a para or ortho to an anionically activated center will form quinomethides. And so you can imagine the stepwise expulsion of HF, not once, but not twice, but 3 times. And then each time water adds in, and finally that hydrolyzes to an acid. So what can we tell these folks to do instead? Well, before we get to those suggestions, I want to mention that the concept of an anionically activated CF3 group is actually generalizable. So there's this OL paper from BMS 10 years ago now, feels like yesterday, where the workers there found medicinal chemistry team led by Jennifer Chow, as I remember, but the famous medicinal chemist Ruth Wexler was also on that paper, found that when they take anionically activated CF3 groups and treat them with one normal NaOH in the presence of, bis nucleophiles, let's say like this amino phenol, the product that results from that condensation is the same as if this CF3 were an acid chloride. And although we haven't learned yet how to make benzoxazoles, there's your first exposure to it. So what do we do to help these folks make the compound? Well, there are a few things we can try. First, instead of using these highly basic conditions, we could simply take the same starting material that they currently have, and we could simply, under more mild conditions, like a simple peptide coupling agent, let's say He2, and apparently, according to the literature, there's a patent on the topic, a compound like this should spontaneously cyclize to give the product with gentle heating. We won't need the acetic acid to do that. That's one idea. There's another idea you could use. So you could take this compound, which is readily available, and use CH functionalization logic. We're allowed to start with the arrow bromide according to the question. And there's a ton of papers. We're going to send everything to this person. There's a ton of papers to get this with using palladium, rhodium. There's 1,000 papers for doing this. Azoles are really easy to do direct hex onto. It's CH, CH activation, if you want to think of it that way. I just think of it as a heck reaction. There's another way to do this, is just think about incorporating the CF3 at a late stage. So you could just use radical chemistry to do that. And the site that you would expect that the radical would go, it's likely going to give you a mixture, but the major product is most likely going to be here. You could use the diversinates, you could use Tony's reagent, whatever your favorite radical forming conditions are to get that product. This will be sent out to the person who asked it with all the literature references in exactly the same way as I would provide in a consulting session. So all of that is actually free, and in fact, you're getting paid to send such questions to the class. So for those of you from industry that are listening in today, you can see no IP was really given. We don't know the company, we don't know the disease area. Your lawyers should have no problem with submitting simple questions like this to enrich the class. So thank you to the person who sent this out. Any questions?
Yeah, Phil, I have a quick question.
Sure.
So in using that first example, instead of starting with the dinitrogen, can you start with the 2-trifluoromethyl aniline and then, I guess, benzylate that and then do a condensation? Would that spontaneously cyclize? Or would you also need strong acid or base?
Are you saying without the other amino group?
Yeah, and condense that onto the ketone, or the ketone of the amide that you're forming.
Are you saying make this compound?
Yes, and then condense with ammonia or something like that.
How do we get the amine here?
Well, I guess my thought was that because it's meta to the CF3, that would be electron withdrawn enough for nucleophilic addition.
No. These are not pi withdrawing, they're sigma withdrawing. So CF3s are terrible activating groups for any kind of direct SNAR. You need the oxidation state here to be something like, even if this was an X, it still wouldn't work. In fact, even if this was a nitro, it's meta, so it's not going to work out for you. So no, you can't. Unfortunately, you're not going to be able to add ammonia into a trifluoromethylarine. It's a good idea, but that's not going to work. We also consider other ways, like from nitroanilenes. The problem is we don't know the identity of this arrow group, so I have to assume that there could be other reducible things on the arrow group. So these suggestions are given with the greatest likelihood of success, with the greatest variability of the AR group. But this is a really good thing, Tim, because we see this kind of thing on the test every year. Don't do that.
Okay, sounds good.
I'm very happy you mentioned that. Awesome. Okay, let's then go on to the question of how do you do nucleophilic addition to various ring carbons we're going to get to that in a minute. But before we get to that, let's talk about electrophilic aromatic substitution on azoles themselves. And I think a good descriptor or explanation for how this works is the classic case of taking NMI and treating it with benzoyl chloride. However, if you take just imidazole and treat it with benzoyl chloride, a completely different adduct results. So the chemistry here is kind of similar to what we talked about with the Dandoni aldehyde synthesis. And I remember Alex had helped us out with that, and she's welcome to jump in here unless someone else is itching to help us with this problem.
I can go for it. So you'll put the benzoyl group first on the pyridine-like nitrogen.
Yes.
But if you have enough benzoyl chloride around, then you'll get functionalization.
How?
You'll have, so you'll deprotonate, and then that anion will be able to add in. And then will that benzoyl group come off just in like a aqueous workup?
Exactly. That's not stable at all. So water is just going to voraciously attack into there without any problem at all. But conversely, something different happens when there's no methyl group. Can you tell us what goes on here?
So the first step will be the same. But then I guess it looks like it's adding into another equivalent.
I don't understand how it does that. What kind of nitrogens are available in this molecule?
The pyridine.
Yeah, I've got a pyridine nitrogen, so why don't you just keep going like you did in the previous problem?
So then that'll just add into, like you'll have deprotonation again, and then that'll add in.
Perfect. Now, this is a really key point that when you form these azoleums, it's really easy to make the corresponding ylid, and those ylids will add into electrophiles very easily. In the case of this one, this is in the protonated form, is a really powerful electrophile. So you can imagine that is dimerizing. You lose one of the benzoyl groups that results before workup, that one, and that gives you out the product. Now, this is a very, very convenient, almost MacGyver-like solution to generate this compound. And I believe there are some companies which still make the aldehyde at the C2 position of imidazole this way. But as you can imagine, all you need to do is hydrolyze this and you get out the aldehyde. No need for bromination, formylation conditions. So a very, very inexpensive, process-friendly way to make the aldehyde of imidazole, which I believe Ulrich did this for many years. They may still do it, but I just don't know. Now, continuing with that theme, we talked about this a lot with the Dandoni. Alex brought us through all of these routes here with azoleum. And building upon that knowledge, maybe we can ask Nick or Debbie, whoever wants to volunteer, how does the famous reaction shown here, which has a name, work?
So you would do Stetter.
And what would I do?
Well, I guess again, deprotonation of the thiazole.
And then?
And then you add into the aldehyde, which condenses through the Breslau intermediate.
And that gives you a product. Stetter, super useful way to do these types of additions to make 1,4-dicarbonyls, which, as we will learn, I think next Wednesday, when we start talking about how to make heterocycles, 1,4-dicarbonyls are phenomenal precursors to pyrols. They form the bedrock of how we think about making a pyrrole. And this is the famous Palnor synthesis of pyrols that we'll cover in a week. Let's talk about nitration tendencies. As we learned from problem of the day number 1, we're going to get nitration here. These two are going to be very easy to nitrate. These two are going to be very, very difficult to nitrate. They're, in general, quite challenging. This one, in fact, there's no reaction. So you can't really get nitration on an oxazole. It's very, very difficult. These other heterocycles are less reactive, but you can probably predict where they're going to go just by thinking about pyridine-like nitrogen, thiophene-like heterocycle, furan-like heterocycle, pyridine-like nitrogen, same logic, pyridine-like nitrogen. And so you can imagine that the result of a nitration event on these is going to be here, here, and here. Now, finally, let's talk about what happens when you start adding nucleophiles onto the heteroaromatic rings. And we can again go back to the classic example of a nitrobenzene. And these intermediates are known as Meisenheimer complexes, shown here. And it shouldn't be greater than, it's roughly the same as a beryllium or a pyridinium salt. And so it's very easy to add in nucleophiles to these species. These add in really, really quickly here, here. Triazines can be added in directly as well. Usually people will add it in, and then upon air oxidation, it will re-aromatize to the triazine. And of course, these, you can get nucleophiles to add into these thiazoliums as well. Now, strong nucleophiles will even attack the more electron deficient heterocycles, such as pyrimidines. So pyrimidines are open for direct attack. Usually you need a pretty strong nucleophile, like a Grignard will do it. It's not a technique which is often used simply because of the harsh conditions and functional group intercompatibility. And pyridine, you can in fact add to that as well. It's kind of difficult to do it directly. You can add lithium reagents to them. It's known as a Ziegler reaction. You can reduce them directly with the lithium aluminum hydride. And there's a sort of dramatic example that everybody knows, hopefully, a famous name reaction. Anybody know it?
Chichi-Bobbin?
Yes, thank you, Simona. So Chichi-Bobbin reaction, since you volunteered the name, can you help us understand how this thing works?
Yeah, so you get a nucleophilic addition of the NH2 minus at the C2. And then this anion can be stabilized by Na plus. And then you get loss of sodium hydride to get your product.
So the world's worst synthesis of sodium hydride. Chichi-Bobbin reaction, not used very often, but it is an inspirational reaction that led other people to develop useful types of reactions, such as the famous example that I can think of, at least, of Hartwig's silver fluoride method for taking pyridines and going directly to the 2-fluoropyridine which was directly inspired by the Chichi-Bobbin reaction. Now, there's another very useful way of adding to heteroaromatic rings. This works on nitro pyridines. It works on nitroarenes of all type. And this is a famous example from the Bristol-Myers Squibb process team when they went about to make gram quantities of the famous alkaloid that we'll talk about a lot in this class called duocarmycin. Do we have any Boger students in this class? Okay, and then maybe they're not raising their hand. How about maybe Fang? Fang over in Florida. Can you maybe guide us through what might be happening here?
Yeah, so first, the potassium tributoxide will deprotonate the chloride. So yeah. And
brilliant. And now what do I do?
Will directly attack the disposition by a SNAR type.
Now what do I do?
And you will be finally deprotonated by tributoxide and form the final product.
And upon workup, as Feng said, we get out the desired product. Brilliant. Now, there's something very interesting about this chemistry. They call it vicarious nucleophilic substitution. You see it quite a bit. It's a really useful tactic to achieve a formal CH functionalization. And it takes advantage of the fact that the oxidation state that you need is built into the reagent itself, a concept we will see over and over and over again when we talk about ring synthesis. So overall, if you didn't have that chlorine, you would need some sort of oxidant. But because the chlorine is there, the oxidant is built into the reagent, thereby eliminating and reestablishing the aromatic compound. So a really, probably the best example I'm aware of out there currently of a VNS reaction from the Bristol-Myers Squibb process team, Mike Schmidt. Great. So let's talk more about pyridiniums, because they are super useful ways of making saturated heterocycles. And a classic example of this comes from Dan Komen's classic use of pyridinium salts to generate alkaloids. And this sort of set the stage for dozens, if not hundreds, of different papers around the world where they use this type of chemistry to start with simple pyridines and turn them into highly decorated pyridiniums. So when you treat this compound with CBZ chloride, what do you think happens, Stone?
CBZ, you form the CBZ add up with the nitrogen.
And then?
And then add into the 2 position of the pyridinium salt.
And then?
And then
we're going to work it up, right?
Yep.
And out comes your pyridone for pyridone product. Now, when you treat this with a Grignard reagent, it has 2 choices. This arrow group can adopt the axial configuration, or it can adopt the equatorial. When it adopts the equatorial configuration, AR here, that's maybe a bad color choice. There's a strong steric repulsion with that CBZ group, so it prefers to adopt the axial. And because of a stereoelectronic requirement, when the nucleophile comes in, it can't approach here. It must approach from the axial side. And so that gives rise to the what you might think is counterintuitive the cis product. And in order to complete the synthesis, all they need to do is some simple functional group manipulations that involve removal of the CBZ, lithium carbonate then cyclizes at that position, and then L-selectride does a stereoselective reduction of that ketone to give the desired product. Now, there is a really nice guide that came out from a former student, Joel Smith, at University of Florida, where he outlines a innate reactivity guide to N-alka pyridiniums and the sort of previously unrecognized phenomena that sometimes these additions can be highly regioselective. In a simple case like 3-bromopyridine, when you methylate it, you see the selectivity is not very good. But when you start putting various substituents for reasons that are sort of at this moment not quite explainable, you start getting useful levels of selectivity. So not sure how to rationalize this at the moment, but the interesting thing is that in the cases where you do get high selectivity, these can be used to very rapidly generate high complexity, as you can see here in their synthesis of this interesting insecticide. Now, one of the, maybe the most dramatic example that I'm aware of taking this Comans type chemistry towards complex molecule synthesis emerges from Snyder's synthesis of cylindrospermopsin. This is a beautiful synthesis, and in order to keep the industry folks happy that are here today, I'm not going to talk too much about the details of the retrosynthetic analysis. I do want to just focus on how they were able to make this compound from the most innocent of starting materials, 3-picoline. That's pretty crazy if you think about it. So we take 3-picoline, and after a few steps, we're going to be able to convert this all the way to A. That certainly should be of some entertainment value to those listening today. So what happens when we take 3-picoline and treat this with H2O2 and acetic anhydride? What do you say, Tiffany?
I guess you might oxidize.
Awesome. And now when we take the N-oxide and we treat this with nitric acid and H2SO4, perhaps Carter can tell us what happens.
Oh, sorry, was muted. Now you can nitrate at the 2 position.
So we have a choice of nitrating either here, here, or here. And you're saying, let's just call this 2, 4, 6.
Well, I would say 6.
Now that's a great point. And I think what helps is to think about the resonance structure of this compound. So that is a dominant resonance form in terms of the way you can rationalize selectivity. So when people make N-oxides of pyridines, and then they do this nitration, which you can find this example, if you check SciFinder, you will find 20,000 hits for it. It's one of the most popular ways of achieving C4 selective functionalization, and almost always people are doing nitration. So there's your surprise answer. Now, when you take this compound and you treat it with potassium carbonate and methanol, something can happen to that nitro group. Any suggestions on what that might be? Maybe they all come from Brendan.
Can you add in methanol to I'm going to say the 6th position.
Awesome. Basically just an SNAR.
Well, never mind. That's not what I said. The wrong thing, but
oh, you said 6 position. Sorry. Yeah.
Yeah. Sorry, but yeah.
Oh, that's great. I'm glad you said 6. Right? You thought the nitro group was very stable and couldn't be moved, right?
I mean, it is a toss-up. It's hard to say.
Well, I'm glad you didn't get it right, because then there's a reason to be here. So, so yeah, when you have an N-oxide, that nitro group is your gateway. you can add any nucleophile to that, and the nitro will gracefully depart. And now, with the only reason that chemistry was enabled was because of that N oxide. Now we need to get rid of the N oxide, and that can be accomplished using H2 and palladium. There's a number of ways of deoxygenating N oxides, but that's one of them. And then with that compound in hand, we're simply going to treat that with the chemistry we know well that we just learned, the Komen's chemistry. And that will give rise to this compound. Now with this compound in hand, we're going to treat this with the vinyl Grignard, and exactly what we talked about with the Komen's chemistry will happen again.
Hey, Phil, from a practical standpoint, is there a reason why they use TROC instead of CBZ?
Because they have olefins and they want to remove the TROC without touching the olefins. Great question. So the TROC can be easily reductively excised, whereas the CBZ will require something like palladium on carbon, and you've got that annoying alkyne and the annoying olefin that is going to be a problem with the CBZ. So redrawn. You've got this compound, which when you treat this compound with zinc and acetic acid, it's going to epimerize this position. And that is going to give you the, after L selectride, compound A that you need. So I think it's an absolutely extraordinary way to think about taking a feedstock material like picoline and converting it to something super useful. So I have proof that this chemistry is useful. For the people on the call that maybe are not able to speak and they're from industry and they're saying, why is he teaching this useless stuff? Here's a consulting question straight out of industry. So using the logic we just talked about now, how do we make that compound? Anybody want to offer a suggestion? We maybe can, let's see, who have we not called on? How about Debbie? Any thoughts? Any thoughts at all?
Well, we can start from the pyridine as we saw right now. We can form the N oxide, then treat with like, you know, form the nitro in the same condition we saw before, and then reduce the nitro after. Not
Well,
now, but maybe.
ultimate. Oh, I see what you're saying. So you want to go to you want to install that nitrogen from the beginning.
Yeah.
Is that what you're saying?
Yeah.
That is an interesting idea. Now, if we just go sort of, we take a step backwards and just retrosynthetically think about how we can simplify this molecule, what is the first thing you would want to look at and say, I want to get rid of that as fast as possible to make my life easy?
I mean, the tetrahydrofuran.
I want to get rid of that, but at a late stage, I do need to worry about this amino group, and I need to worry about that stereochemistry. These are things I need to worry about.
Yeah, so basically we have to use exactly the same type of sequence we saw before.
And in order to use that sequence, I'm going to require that this becomes a carbonyl group, right?
Yeah, that's right.
Okay. Because I know there's 100 ways of doing reductive amination to give me the right stereochemistry at that position. I can use kinetic, thermodynamic conditions, whatever, bulky, reducing agent, and I'm confident that I can get that. So now I need to be able to put this together, and it's probably going to come from a compound like this, wherein copper, yes,
and then we attack there.
This oxidant can be MUF, it can be Davis oxyuridine, and that would give you So the trans delivery when you do a vicinal difunctionalization. And all we need to do to finish is what?
Well, we can like,
I've got to install a hydroxy here, don't I?
yeah,
So I can do a hydroboration.
and then just SN2, yeah.
Selective tosylation of the primary alcohol, and then treat with base, and it should slam shut to the THF ring. Great. So when you're making, one of the ways of thinking about, we have a whole class this year on saturated heterocycles. And one of the common tactics of making more complicated saturated heterocycles is going to be thinking about how you can get back to it from a pyridine. So that's a key lesson there. All right, let's talk about haloselectivity. And a good way to start off with haloselectivity, again, this encompasses a ton of different consulting questions I've gotten over the years, is how do you think about putting the molecule like this together? Anybody have some suggestions on some thoughts, what they might do here? Maybe some building blocks? We need a good medicinal chemist. Maybe Ellie.
Yeah, so I think that you have to, or I was thinking of starting with like where you see all of the added on amines have chlorines there, and then maybe doing some sort of like Buchwald, Hartwig.
Nice. That's wonderful. Wonderful idea, Ellie. That is exactly the way a medicinal chemist would think. Now I have a question for you though, that might be a little difficult. I need to add those amines in. You said Buchwald Hartwig, but I'm going to counter with, how about just SNAR?
Yeah, that would work.
Because you can use transition metal catalyzed amination when it strategically makes sense. We'll talk about that when. But when the compound is innately primed to do the chemistry already for you, there's no need to break out your bottle of palladium yet, or copper. So in this problem, we have a trichloropyrimidine, Ellie. And obviously, if you're a medicinal chemist doing this stuff, you're going to have a challenge with regards to the regiochemistry. So is that going to be on your mind as a problem, or do you think that this is going to be okay? And if it's okay, what order do I add the things in?
Yeah, I think it's gonna be okay.
Okay, tell me how. I'm going to label for you. So let's label it.
Yeah, thanks. So I think 6 and 4 have similar reactivity for SNAR, and they would react first.
Oh, that's really nice. So I'm going to abbreviate this by saying A. I'm going to call this one B. I'm going to call this one C as our 3 amino components. And what you're telling me to do is add in A first. If I'm understanding you correctly.
Yeah, and then B and then C, I think.
So you're telling me in the next step, and maybe we need somebody to, maybe we need some audience participation. There is a 2 position and a 4 position, and you're telling me it's going at 4 next.
Yeah, I thought so, because it's like
Or
ortho to one pyridine and then para to the other pyridine nitrogen, but
certainly sounds reasonable. Anyone have does anyone think C2 might be the right answer?
Yeah, I think it's C2 because suddenly you have an electron donating group at your A position.
Well, shouldn't C2 is the one be the one that react first when you combine with A?
Oh, wow. There's even some debate as to whether our first one is right. So we may be in a lot of trouble. So Some people think C2 is going to be the first. Some people think that they're okay with C4 being or C6 being first, but then there's this sort of debate as to whether C2 or 4 are going to be next. You can imagine if you're going to be interviewed at a company one day, you probably should know exactly what's going to happen. And luckily, the rules are available for you. So the first step is correct. Ellie is 100% right. When you have a 2,4,6 pyrimidine chloride, the trichloride, the 4 and the 6 react really quickly first. The second one to react is going to be C2 for roughly the reason that Simona outlined. And then finally, that's your product. Now, haloselectivity is a really important concept in heterocyclic chemistry. And trying to rationalize what halogen will get attacked first often encompasses the way you will design your entire medicinal chemistry program. Medicinal chemists love polyhalogenated arenes. Process chemists hate them. So polyhalogenated arenes for process chemists is bad for a number of reasons. You'll sometimes see it be done. We'll talk about examples where it's done, but in general, they want to avoid the halide waste, and it also is a different type of thinking. So medicinal chemistry, all they care about is getting to diversity as fast as possible, where each step is modular. So as you can imagine, if we were going to make a tri-substituted pyrimidine, a modular cassette-like approach where you've got 3 halogens and you dump one thing, dump another thing, and a third thing is going to be pretty much 100% ideality from the standpoint of a medicinal chemistry program and exploring diversity around a ring. A process chemist, though, may look at such a problem and say, you know what, we need to start with building blocks that don't have this chloride and simply build the exact target we want. Such an approach might be beautiful to a process chemist, but an approach like that would be a horrific nightmare for medicinal chemists. So haloselectivity is probably more important for a medicinal chemist than it is for a process chemist. Now, it turns out that when you're thinking about SNAR reactions on a pyrimidine.
Sorry, can I ask you a question about that problem?
Sure.
So when you're adding A versus B, you add the morpholine last because if you added it first, does that have the potential to react in the next couple steps? Like, why specifically would you add A first?
I believe the reason you would add that one first is because it is the least reactive of the amines.
Okay.
And so you want your SNARs to be as rapid as possible. And an aminopyrazole is like an aminopyridine, far less reactive than a morpholine.
Got it.
So these chemists realize that the morpholine can be put in last simply because it's going to be super reactive. As you add in nitrogen nucleophiles to a trichloro-pyrimidine, it becomes less and less likely to do SNAR. The conditions are more and more forcing. So that first conditions, you can imagine the temperature is low, then a little bit higher, and then a little bit higher. Okay, so you'll want to plan out these routes based on the basicity, nucleophilicity of your nucleophile, as well as the perceived haloselectivity in the reaction. Now, this is SNAR, but the rules often also work for oxidative addition when you do Suzuki reactions or Buchwald-Hartwig reactions. It's a fairly complex topic, and it can be, in some cases, rather idiosyncratic with the heterocycle and the nucleophile you use. But there are some hard and fast rules that you can use that we'll talk about. Let's do this consulting corner where we talk about haloselectivity in general. So in the case of a 2,6-dichloropyridine, let's see, how about maybe Sung-Han, any thoughts on a 2,6-dichloropyridine? which one goes first?
I guess 2.
So if I'm doing a Suzuki coupling, usually 2 position goes first. If I do an SNR reaction, it's nucleophile dependent. I can sometimes get 4 or I can get 2. But in general, the literature shows that you're going to get more C2 for transition metal catalyzed cross coupling. What about the case of 3-chloroindole? We need an indole expert, and maybe Tanner, if he's on the line, can help us.
Yeah.
Yeah, tell me about the 3-chloroindole. Can I just add in a nucleophile to this? Let's say I want to add in.
This position should be already pretty electron rich, so maybe no.
Yeah, I'm going to be out of luck. I see this a lot, and people are like, well, my Buckwalds are not working. And the reason they may not be working is simply if you're even able to make that product, it's not going to be very stable. When you generate that product, as you can imagine, that's not a very happy compound. We talked about why already on Monday. It's a pretty pi excessive heterocycle. And so likely this compound is simply going to hydrolyze and deliver to you that. So don't try to do SNAR reactions. We see this in a test every year. People try to do SNAR reactions on heterocycles just like this. Stop doing that. If you want to do it, you have to have an EWG. Then it's okay. Okay? We already talked about this case above. In this case, this is one of medicinal chemists' favorite starting materials because you can dump in the nucleophiles one at a time. Unless you have a very reactive system, amine, for instance, you can sometimes get bis addition, but usually it goes cleanly mono, bis, and tris. Now, this is an interesting case. Can I take 2-aminopyridine and simply convert it into, how would you do this? Let's say I want to do a Suzuki reaction. Or let's say I want to add a nucleophile into a 2-aminopyridine. Is there a way to do that? What do you say? Aaron, any ideas? Or Stone?
Form the diazonium or beryllium salt.
Aha. Diazonium is a good idea. It's a classic way. You could do Sandmeyer. But the beryllium one you mentioned is a newly emerging strategy. Former student Pep Cornella has a really powerful way of taking these berylliums and adding all sorts of nucleophiles into them. And this is a really powerful way of thinking about an amine as a placeholder for a halide or a halide surrogate. People often don't like Sandmeyer because of the conditions can be harsh or not functional group tolerant, particularly if you're in a really complicated heterocycle. So for the medicinal chemist on the line, this is a very useful method for you to remember. Pep already published a paper in Agavante, but there's also a ChemArchive deposition from a couple of weeks ago where he shows that the nucleophile can even be things like a chloride or a bromide. So very simple, mild way of taking an aminopyridine and converting it into a halide for subsequent cross-coupling, or adding in a sulfur nucleophile or an oxygen nucleophile or another nitrogen nucleophile to replace it. Let me ask you a question. Would this reaction work? Am I gonna see this on the exam? Simona, are you gonna put this on the exam?
No,
Why not?
because that position is too electron rich.
Yeah, so this technology can only work when you've got adjacency to a pyridine like nitrogen. Please don't do this on positions which are not activated. So the same goes for, we talked about on Monday, the pi prop chemistry. Same thing goes for that. So if I try to do pi prop and some cross coupling on that, it's not going to work on the 3-hydroxypyridine. It's only going to work on the 2 and the 4. Great. How do you control? Yes.
So with regard to the trichloropyrimidine case,
yes.
Essentially, the one that adds in first in the SNAR is basically the one that is relatively in a 4 and 2 position in comparison to the one that is double 2 position.
Correct.
Whereas, for example, for 2,4-dichloropyridine, the one in the 2 position is more active in transition network cross coupling. So is that the same for the pyrimidine, or is it different?
No, in case of, like I said before, almost always the rules of SNAR track evenly to the rules of cross coupling. Almost always, but there are a couple of cases like a simple 2,4-dichloropyridine where those rules can be somewhat nuanced based upon nucleophile and conditions. And in fact, Suzuki's, in the case of a pyridine, will usually break that rule of the SNAR. But certain SNARs, depending on your nucleophile and your solvent and your conditions, will go at C2 instead of C4. So I'm going to talk more about these nuances in just a moment. But to sort of get to that point, I just want to point out 2 things. Before
Can I jump in with a question before you move on?
Yeah, please do.
You drew out a pyridinium, but you said beryllium. Would either work, or?
So what I meant is that this is derived from a beryllium. Sorry about that.
Wait, I'm sorry. Can you explain what you're saying?
So if I take beryllium and I treat it with a amine, I'm going to get an addition. We're going to actually cover this down below. Get an addition, a loss of water, and it exchanges it to make a pyridinium.
Okay, thank you.
Yep, and we're going to cover that in just a minute. Great point there, Alex. I sort of jumped the gun. So how about the case of a compound like that? Where is that going to go? Well, as it turns out, the literature suggests that soft nucleophiles will add here. Hard nucleophiles will add here. And cross-coupling will take place here. Here's another example for you before we get to a broad overview. In this case, we can do Suzuki here first, followed by SNAR here. And in a case like this one here, if you've got a bromochloropyridine and you want to control where the amination is going to go using palladium, the Sigmund group found a way to use ligands to control selectivity. So they showed how they could use one set of ligands in order to get 2-chloro reactivity and another set of conditions to get 3-bromo reactivity or 5-bromo reactivity. If you didn't know these conditions existed, I suspect it might be possible to simply take aniline and base. If you put this on an exam, it would be 100% right. Because again, for the same reason that Simona mentioned, that bromo is not activated, but that chloro is like a quasi-acid chloride. So sort of the future, I think, of this type of haloselectivity will be using ligands to override innate selectivity. Now, we did a great group meeting on this topic 10 years ago by Will Goodkunst, who's now a professor at Georgia Tech. And in here is a lot of a summary by a lot of the work that a individual, Scott Handy, did many years ago, where just like the ChemDraw prediction software I showed you to predict electrophilic aromatic substitution, the Handy method is actually a truth in advertising, a handy method for figuring out the site selectivity of cross-coupling, wherein you can use the proton spectrum to predict, based on which one is higher field, which one will undergo cross-coupling first, second, and third. But this group meeting is a great summary that Max will send to you. It's also available online for the visitors. That summarizes really in a lot of gory detail the details of haloselectivity, which make up a large portion of consulting questions that are out there. What about the case, going back to Simona's point of these 3 bromo or 3 activated systems being kind of dead? Well, what happens if I push it? What happens if I take 3-bromopyridine and just push it with sodium amide? Any ideas what might happen?
Maybe like a
sure.
benzene.
Sorry, I can't hear you. What do you say, Brendan?
Maybe like a benzene, because it won't add in. So maybe it'll just eliminate the HBr, the bromide.
Exactly. So pyridine, exactly. Pyridine can be very useful. A lot of great work from the GAR group over the past few years and others on making and employing pyridine in their chemistry. Okay, so we have about 10 minutes left, and in those 10 minutes, we're going to cover rather strange additions to heterocycles. And so nucleophiles adding into not only pyridiniums, but other types of heterocycles that are not that aromatic or have an ability to undergo ring opening and addition. So for that, let's take a look at problem of the day number 7, where we need someone brave to tell us what is going on when we treat this with hydroxide. Somehow it morphs itself into a pyridone that is no longer a pyridinium. So who is going to volunteer for this one?
Well, I can go with it.
All right, great, Yonan. What do you say?
So you have the hydroxide adding to the C2 position of the pyridinium. So then that will give you the structure that is similar to the hemiacetal. So then it can ring open from to form the ketone and the enamine. Yeah, then you have the bond rotation, and then the nitrogen just attack the ester group, and you have the pyridone product.
Brilliant. Awesome job. Does everybody see that? Great. What happens when we... Okay. What happens when we take oxazole and we just boil it up with formamide? What might happen there?
If we're using the same logic, we're
We
just
are.
going to go from the oxazole to the imidazole. So nucleophilic addition into that, and then you get into C2. So then you have your ring opening and then ring closing, and you lose water to reamortize.
And prior to the workup, there was a CHO group here, which just cleaves nicely upon workup. Same kind of logic again here in the next one. Maybe Tim, you just want to shout out what is the product of taking this isoxazole and treating with hydrazine. What might emerge from that?
Your pyrazine.
Just a naming issue. Pyrazole. The isoxazole is simply a 1,3-dicarbonyl compound that is hiding. It's hiding. When we talk about oxazole synthesis and isoxazole synthesis, we'll talk all about that. But you can imagine it's easy to exchange that with hydrazine just by cooking it up. Let's move over to the other side. Same exact logic for this one. And it's actually kind of similar to the Chichi-Bobbin reaction. So we're going to add KOH into this. We're going to continue to heat it for a while. Throw the ani in there. Loss of hydride. Basically hydrogen. After workup, we get out that. We just talked about this. Alex, do you see how this is working?
Yeah, so kind of the same idea. You'll have it add in and then open up.
When we talk about berylliums, this will be kind of important. How about taking an N oxide and treating with acetic anhydride and then water? What might be the product of that? Kelly?
Pyridone.
Oh, who is that? Nick?
Yeah, I said the pyridone. It's the Berkeley rearrangement.
Well, I'm glad you said that because it's not the Berkeley, but it's something very, very similar to the Berkeley. So this goes via and then after workup, you get that, right?
Oh, so it's not intramolecular.
Is it intramolecular? I mean, okay. Let's imagine you can draw it that way. I know the geometry is right for this. So no, usually people invoke the formation of the C2 adduct followed by loss of acetic acid, and then upon workup, the OAC cleaves to give you product. You're thinking of something different. And so I'm thinking that when you said Berkeley, what you're recalling is a reaction that takes the methyl group here.
Oh,
And
that must be the one. Yeah, okay.
that is the Berkeley, a very useful way of doing CH functionalization of alkyl pyridiniums.
Right. That one is the intramolecular one.
That
Yes,
one
that
is,
makes sense.
yes, exactly.
It's membered. Yeah. Okay.
And this one is via and that's how you get that. So this is the Berkeley. Very useful reaction for functionalizing methyl pyridiniums. Now, what happens when you take pydrop and a nucleophile? Any kind of coupling reagent, dehydrating reagent, tazole chloride will work too sometimes, but in general, this is a really useful way of taking N oxides and priming them for attack with loss of the corresponding N oxide. And this is a very interesting reaction called the Bamberger reaction. And the Bamberger is important because it's actually used in protein labeling. It forms the basis for why histidines label really well under these types of conditions. Not with benzoyl chloride, a different electrophile. But can someone sort of shout out what the product of this Bamberger reaction might be? It goes back to a problem of the day that Alex worked on earlier. She's welcome to opine on this, or someone else can jump in. I'll give you a clue. The base is usually with water present. You can do it in a buffer solution if you want.
Do you get the one, sorry, the
Go
1
ahead.
2 amino?
Yes. So the intermediate bis benzoylated compound we saw before can be attacked, and loss of formamide gives you your cleaved product. The Bamberger cleavage, extremely important if you're in chemical biology. That's how they label, in a lot of old cases at least, they probably still do it today. That's how they label histidine. And we have 1 minute left, and I'm just going to point out that the zinc A reaction is shown here, a really useful way of excising the nitrogen on a pyridine and putting anything in its place that you want. And you can work out the mechanism on your own. It's pretty much identical to problem of the day number 7 that we already covered. So the new nitrogen nucleophile will come in, ring opening, ring closing, loss of dinitro phenylamine, and you get a sort of metathesis of one nitrogen into another. And we'll end the lecture right on time with the classic reaction known as the Reicert. Can someone call out how this works? It's very similar to Komen's chemistry. That's your clue. Who wants to bring it home?
You acylate the nitrogen, and then your cyanide anion attacks at the 2 position.
And this type of reaction can even be done in an enantioselective fashion, dating all the way back, I think, 20 years ago to Shibasaki's work. So a lot of applications of the Reicert reaction in synthesis. We will see it again when we talk about isoquinolines in a few weeks, I guess. So with that, folks, keep your consulting problems coming. We really enjoy them. A lot of Dogecoin given out today. And have a great weekend. And we will see you on Monday for the last installment of Reactivity before we get into how to make these ring systems. So talk to you soon, folks. Take care.